Alright, so I got a little bit more charge on this. Let's take a look at the voltage. And it's 17.8 volts. So let's check this out again and see what happens. And we got 19 milliamps, so about 20 milliamps at idle. And some people may say, well, maybe the meter is doing it. Well, let's turn the meter on. It jumps up to 26, and it's only got one LED lit. Once it turns off, it goes back down to 19. And just so you see what I'm doing, I'm just running checking current this way. So that's kind of interesting. Let's check the voltage across all these. 3.56, 3.56, 3.56, 3.56, 3.56, well, 57. Okay, so I don't have a microscope, so I had to make something to get me by. This is just a webcam. It's been modified so that it can focus on things much closer. A little light and a little 3D printed contraption to hold it in place. And yes, this is poster tack and a roll of electrical tape to hold it in place and hold it level. So let's take a look. So now that I've actually been able to read the ID code on the diodes, I'm noticing it says Z24V. You know, that's upside down obviously, but Z24V, which means that's a Zener diode. So that changes things a little bit. So let's back out of here. Take out the digital zoom. And let's move this over a little bit. And I got to get rid of this little orange. You'll see the reflection right there. Where is it at? Yeah, I got to get used to this. You'll see the little reflection of the orange light from the webcam. I got to disconnect that because that's going to drive me nuts. But if we measure the diode, see if I can do this. Oh, I don't have it in diode mode. So if we measure the diode, we get 0.5 volts. And we go this direction, we get 2. Now we should get 0. But this is in circuit, remember. So these here, this goes down to a capacitor. This goes over to another capacitor, and then it shorts back out here. But these capacitors should block DC voltage. So there might be something else in here that's doing it. Like if you look, it comes over here, and there is a couple resistors up here. So this goes to there, and so I'm going to do my best and try to get one of these out of here and test it out of circuit. And I don't, like I said before, I don't have hot air. The way to actually properly test a Zener diode, there's a couple ways. This is just to see if there's any leakage. So one direction you should see a certain voltage, another direction you should see no voltage. So what I have here is I have a bunch of Zener diodes, and this is the exact, or should be the exact diode that is. This is just a different package type. This isn't a surface mount device. So if we measure it this way, you notice we have nothing. It's infinite. But if we spin it around and measure it this way, we get 0.7. And that's the way it should work. Now there's another test that you can do, and I'm not too worried about that at this moment because I just want to make sure that the reverse bias of this isn't actually 2.1 volts. It should be infinite. It should be 0. The other way is perfectly fine. 0.5 is just right. Now this tip is a little bit too big for what I'm doing, but what we're going to do is just try to pull some solder around it. And this iron's a little bit too hot right now. I'm waiting for it to cool down. I changed the temperature. There. So we're going to add some extra solder to it. I'm going to let it cool down just a little bit. So now that it's just lifted, that's actually even better. I can go in and test it. And I'm getting nothing, which is good. Let's try the other way around. And I'm getting 0.6. So these diodes, I'm going to guess, are fine. On second thought, they are connected in series. Let's check them all. Alright, so let's test this one here. So we got 0.6 in that direction. And I got nothing in the other direction. So that's good. So let's go put this back on. And I just overheated and broke the diode. That's okay. Alright, so I tried to solder a regular through-hole Zener diode to these contacts, and the problem I'm kind of worried about is the cells actually lay right up against this board, so I don't want anything that's going to be sticking out too far. So I looked, and actually this lead right here goes right to ground, and then this one comes down here, and there's a via right there. If we flip the board over, I've already actually tested it, but I'll show you. It's test pad 23. Goes to, where is it? The other side there. And I know I can't show you that too easily, but it does. So what I'm going to do is simply run a diode from test pad 23 to ground. So this here is ground. So I'm thinking if we just run the diode this way, we solder it there and then clamp it down there. And then over here, I really don't even have to cut this side, but I will. And we get same thing as before. So that's good. I mean, that's what we want. We didn't want to disturb anything. We just wanted to put it back after we found out that those two diodes were good. So I had to step away for a little while. So I'm not sure where I left off, but I believe we were testing these diodes. So I replaced the diode that I broke here and placed it on the other side of the board using just a full-size diode. And now we have these two items here to check out. Now I looked this one here, and I can't bring it up on screen because it's on another computer right now. It's a long story. But this one here is a N-channel MOSFET, and this one here is just a diode pack. So there's a diode going from here to the center, and then a diode going from here to here. That's easy enough to test. I'm just going to do basic. I'm not going to spend much more time on this. I just wanted to get a good, a basic idea. I have a feeling at this point that it's A, a bad design, and B, the cells are pretty shitty. So the most basic test that you can run is just place your meter into diode mode and place the negative, which is this one here, on the drain, which happens to be here on this, and the positive on the source. And you should get anywhere between 4 to 9, or 0.4 to 0.9 volts, and we have 0.452. So that's good. So it actually does check out there. Now another way to test these is just to do a resistance check. regardless of the polarity, there should be a pretty high resistance, and it's about 3 mega ohms. So that's pretty high resistance between the drain and the source, and it should be the same regardless. Now another way to test this is just to do a simple resistance check between the drain and the source, which is what we just did, except in diode mode. So this is showing 2 mega ohms, 2.1, and it shouldn't really matter the polarity. The reading will change, but it'll still be an absurdly high resistance reading. See, it's even higher now. So if we also go between the gate and the source, it should also be a high resistance. And it is. Now you can check the data sheet to see exactly what this is going to be, but like I said before, I'm not spending too much time on this. I'm just doing some quick checks. And we can also check the gate and the drain. And again, high current. So nothing is shorted out, or doesn't seem to be shorted out. So we're going to go back to diode mode and just test this. And we get 0.566, 1.6, and again, this is in the circuit, so just like before, really not going to see too much. 0.6, 0.5, 0.6. So yeah, it's acting like a diode, and again, it's in the circuit. Really can't tell, and I'm not removing that. So I'm fairly confident that those components are okay. Now what's left is these two ICs down here, and I have tried and I've looked, and I cannot find any information on them. Going by the markings that are currently on them, and just by looking at the way that this whole thing is wired, this whole circuit here is for load balancing. Now generally the load balancing is going to happen while it's either charging or discharging, but it seems as though this is actually active all the time, that these ICs are running and pulling current at all times, which I'm starting to believe is just a bad design. Here's how we figure out the battery life of something, or at least this is one way of doing it. What you would do is take the battery capacity, which is 2,000 milliamps, and you divide that by the load current, which is 20 milliamps. Then you multiply it by 0.7, and the 0.7 is more or less a fail-safe. You're not going to be able to run the battery all the way down to 0 volts. It's only going to go down to about 2 volts before the charger shuts it off, or at least it's supposed to. Doesn't really know if it does. Also, it takes into account any kind of external factors, temperature, etc. If we just did 20 into 2,000, we're going to have 100 hours. Once you multiply it by 0.7, we get about 70 hours. Now that's with just that load. If the batteries themselves are dying, it's going to decrease that even more. So, within 48 hours, a little bit over 2 days, 2 or 3 days, hooked up to this board, this battery is going to be completely dead. So really, even with a brand new pack of batteries, this is going to pull 20 milliamps all the time. And math doesn't lie unless I'm doing it wrong, and if I am, somebody please tell me. But you're going to get 70 to 100 hours, of time before this actually drains batteries out completely.